Hi, this is the last bit of life table module, so we'll finish it today. So in this module, if what we will look at the expectation, like lifetime expectation over an n period, not the whole life, but over an n period. But just to recall, if you recall what we did last time, right? We calculated EX, and this is for the discrete case, right? We calculated EX. We said it's a summation of k plus 1 px, right? If you remember, k plus 1 px, and we said from k equals 0, right? And when we did this one, we created a table. We created a table, right? If you remember, we created a table and then we computed it. And this is basically, this is the whole life, like life expectation at age X. This is whole life, like the whole life expectation till death. But a new term now we will introduce it is, we wanted the expected lifetime, how many years over n years. So basically you insure an individual for 5 years, you would see how much, like the expected life expectancy over the insured period of 5 years. So n is 5, right? So this is not the whole, you not sum, like here you sum all the way to the end, or here you sum from k equals 0 to n actually, right? Because you sum with k plus 1 px, right? You sum it for just like the n terms. But just like maybe easier to look at it this way is simply you take Lx and then you take Lx plus 1 and Lx plus 2 all the way, you add for Lx plus n, right? And this is because Lx plus 1 over Lx, this can be here it will be 1 px plus 2 px plus 3 px all the way. Last one will be n px, right? So you have the probability of survival for every year, right? All the way to n, right? This is exactly the definition. But let's take one example. If you remember last time we looked at the table x 96, 97, you know, and then we have Lx given to us. But let me present it this time, you know, last time we did it with a table. Let me represent it by this line. So we have 96, 97, 98, 99, 100. So this is now, we were given, I think it was 180 new lives here, then they reduced 130. This is the example from last slide, 73, 31, all of them, they died by 100. So we calculated the expected life, the whole life, but now what we are interested in is calculate the expected term life expectancy, the term life expectancy, so not the whole life, but the expected remaining lifetime over the next 2 years only. We follow the definition here. You can either choose this one or this one, right? I'll use the Lx, so this one will be divided by our 96, L96. So remember, the first one you add 1 to it, Lx plus 1 all the way to n. So now you have Lx plus 1, so 97, Lx plus 2, which is your n. And just to remember, here you have 2 years, so you have 1, 2, right? It cannot be more, right? You need to be very careful about it, right? It's simple. There is nothing difficult here about it. And this one, right, you can calculate it to be your 180. So you take 100 L97, this one 130 plus 73, which gives you 200 or 3 over 180, right? So the expected value of life 203 divided by 180 is 1.1278. So what does that mean? It means that for the remaining for the next 2 years, the expected remaining lifetime for the next 2 years, it will be 1.127. So on average, this cohort, they will live within the next coming 2 years, they will live on average 1.1278, right? But I know we talk about the about discrete distribution, but I kept this topic from the continuous distribution to this time. So I think it's fitting, you know, based on, because it would have been difficult if I introduce it earlier. But I will introduce also now. We'll come back to the to this one now, the continuous x over next n, right? So we'll introduce this one. This we continuous, right? And let's look at it, this one quickly. So remember what we said, recall what we did last time. We said ex continuous, we have from 0 to infinity, and you compute tpx, right? dt, right? Now if you want the expected remaining lifetime over n period, it will be simply from 0 to n. Now tpx dt, simple. You don't integrate it to infinity, you integrate it only to n, right? And this is something we need to keep it in our mind. Let's take a few examples here. As always, it's the easiest thing is to do is, let's do let's take the one easy function, which is the constant force of mortality. So TP, let's say 10, is equal E minus 0.10t. So your mu, the mu here is 10%, right? And the question here is to find E10 for 5 years. So the expected remaining lifetime for the next 5 years, right? So the remaining, so we are interested remaining lifetime over next 5 years. Simple. We follow the logic 0 to n. tpx, what is tpx? It's already given to us, so it's easy. No, t dt. Right, so that's very good because now we can calculate it quickly. So 0.10, 1 over this one minus, and then you have, if you plug in your n, it will be, sorry, our n here is 5 years, right? If you plug in your 5, it will be e minus 0.5 subtraction, and you plug in 0, it will be e minus, well, I mean, you can write it just 1. So this one, E10, if you use your calculator, which I will do in a second. So you see, like always use the same calculator. So what I will do is e to minus 0.5, subtract from it 1, or divided by 0.1, or multiply by 10. So 3.935. So for a life that is distributed following a constant force of mortality with mu is 10%, then for the next 5 years, the expected life, or the life expectancy over 5 years, it will be 3.935, right? Just let me pause and reflect here, because we have little insight here. Let's look at the relationship between things. E10. Let's see the relationship between this, and then we have E15, right? Let's try to equate them. So if you, for this is constant force of mortality, mu is 10. So this one will be 1 over mu, which is 1 over 10, it will be 10, right? This one we already calculated it. 3.935, right? This one, because this is constant for some mortality, it's the same thing. It's 1 over mu, it should be also 10, right? If you want to equate them, so this will be equal this, and this multiplied by this. There is little bit of thing we need to add here, which is 5p10. Sorry, I meant here is a plus, and this is multiplied. And if you want to verify it, 5p10, this is a constant force of mortality, so it's the mu minus 5 times the same 0.1. Let's calculate, double check it. You will see that all of them, they give you the same answer, right? I don't want to calculate, well, let me do it just to double check. In case I made a mistake, I can correct it right away. Correct. I got exactly the same answer, right? So this is very good, right? So this is very good. So let's generalize it in general. Let's generalize this relationship. If you have EX, this can be equated by EXN plus NPX, okay, multiplied by E2, now X plus N. It's something, it's very good relationship to keep it in your mind. It's very good relationship to memorize it, because sometimes, you know, like I can ask question to play with it, and if those, they will take actuarial mathematics, it's a common question that in this exam that you'll have something that is built on this relationship. So it's good to know this little relationship. Let's take another example related to this one. Let's take another example. Let's take or verify our this one based on another question. Let's take S of x. Now uniform distribution is 100 minus x divided by 100. The life is it's over 0 to 100. So the life here is uniformly distributed over between 0 and 100, right? So this is very easy, right? So the question here is to find, and we wanted E10 for 5 years. So I wanted to find the expected life expectancy for somebody's at age 10 for within the next 5 years. Right? This one, it's quickly we can calculate it. It's 0 to 5 TPX. Our TPX, well, I mean, this can be written also. Well, let's step by step. So what is P10? Remember, if x is uniformly distributed, the remaining lifetime is also uniformly distributed, but over omega minus t, right? This, we've done it so many times. So TPX will be, instead of 100, it will be 90 minus t over 90. We did it many times. The remaining lifetime is uniformly distributed. For somebody reached the age 10, the remaining lifetime is distributed over 90 years, right? For t between 0 and 90. This one, it's maybe easier to write it t over 90. So now we wanted to calculate 10 for 5 years, 0 to 5, 1 minus t over 90 dt. We can do it quickly. It's not, so this will be t minus t to 2 over 180, evaluated between 0 and 5. So E10, not to read it 40, this is 10 for 5 years will be fine. So 25 divided by 180, oh sorry, 25 divided by 180. Yeah, I got 4.8611, right? So for a life that is age 10, the expected lifetime for the next 5 years will be 4.861, right? 1. So what we wanted now to do is to look at also our relationship that we looked at. At.the. Let's verify using this relationship. 5p10 multiplied by E15. E10 for uniform distribution is, right, it's if you would take this one for uniform distribution over 90, it will be 90 over 2, it's 45, right? Quickly, because remaining lifetime is 90 years. You divide, like omega is 90, you divide omega by 2, right? It's just like, not to forget, omega minus x divided by 2. Now let's look at this one. This one already we calculated it to be 4.8611. 5p10 tpx for 10 we already have it here. TP10 take 10, it's 80 over 90, right? 85 over 90 using the formula. Now E15, now omega here, same thing, omega minus x, it will be 85 divided by 2, 42.5, right? This one, omega minus x divided by 2. Now x is, here is 15, and this is 100 for 2. Did I get it right? Verify it, it should be also okay. If you multiply it, it should be okay. Let me, on this relationship, let me tell you, like this is was actuarial exam one of the years. So let's take x is modeled. What is x? It's the random variable, the lifetime random variable, as following. It's a very good question. This one is a very good question. So x is modeled as following. So for it's modeled as uniform over 0 and 100. So x is uniform over 0 and 100. For x, for the first 30 years, x is uniform. So for the first 30 years, x is uniform, right? For the first 30 years, x is uniform. Now for the next, for the after 30 years, it's constant force model with mu equals, mu is a force of mortality 2% for x greater or equal 30. It's continuous distribution. Yeah, let's give this. Yeah, it doesn't matter, right? It doesn't matter because it's continuous distribution, right? So what I wanted to say here is like this is a unique model. Here you have, if you would consider, let's have, you know, s of x for this creation. S of x will be, actually you will have two functions for x between 0 and 30, and then you have for x greater than 30, you would have this one, it will be it's uniform distributed over 100, so it will be 100 minus minus x over 100. This one here will be, yeah, I mean it will be, you need first to survive S30 from here, and then well, let's not do it this way. Why you need to do this way? Forget about this way. This is the hard way. Why I'm doing it the hard way? Since I gave you the easy way. The easy way is we use this relationship. We use this relationship. We don't need to do any integration like of the new s of x. So let's do it the easy way. Let's not complicate it. When it's easy, let's not complicate it. So what is the easy way is simply to recognize that we wanted, the question is to ask, oh, well, I didn't say what's the question. The question is to find e of 0. So E0, instead of integrating, like creating s of x that makes distribution and integrate it, we can recognize it as, we can split it between two terms. One is E00 for the first 30 years, and then we have 30 P0 multiplied by E30. This is much easier, right? Instead of if the other way that I was about to do it the hard way, it will take us long time and you create a messy survival distribution. But if you know this relationship, you can just quickly do it this way. So for the first 30 years here, we need to do this one by one. Let's do the first one. This one is from 0 to 30 for TPX, right? DT. And TPX here 0. And this is because it's the first 30 years, so we take 0 to 30. And this is uniformly distributed over 100. It's given in the question, so it will be 1 minus. This I don't want to keep repeating it. It's for uniform distribution. S of x is 100 dt, right? For uniform distribution, you need to know what is s of x, what is quickly. You don't need every time to derive it, right? If you do this one, it will be t minus t to 2 over 200 from 0 to 30. So we do your calculator. So the first term you get is E00 for 30 is 4.5, right? So this is the first term. This one is done. Now let's look at this one. So to survive 30 years from time 0. So 30 survive 30 years at time 0. It's again, this is the first 30 years. The first 30 years, the question tells us it's uniform. So uniform over 0, 100. So to survive it, I mean, you can right away answer 70%, right? Because your TPX is 1 minus T over 100. And our T here is 30. So now we got second one here. Now we need to get this one. This is easy, very easy. E30. This is it's actually, because it's constant force of mortality, it's the same thing, right? It's 1 over mu. And our mu, let's look up what is our mu here. 0.2. Right, so it's 50. Easy. So now we got the 3 terms, so let's write it again. So if you want E00, we split it into, because we have the distribution is split, so we need to take each term by itself. So the first one is we take E0 for the first 30 years, then we survive the 30 years, and then we take E30. So this one we already calculated to be 4.5 plus This one we calculated to be 0.07 plus multiply by 50, right? If you do this calculation, well, I mean, it's quickly 60.5, but let me double check. So we have 0.7 multiplied by 50, 35, plus, oh, sorry, here, no, I made a mistake here. Doesn't make any sense. This cannot be. Let me double check it. I made a mistake for this one. It cannot be. Yeah. So it's 30 minus 4.5, 25.5. Sorry, correct your note. It's for this one, for the first one. For this one is 25.5. I made a mistake just in the multiplication, right? But it cannot be, you know, it cannot be that you have 4.5. It just doesn't make any sense. 25.5, right? So now it makes sense. 25.5 plus 0.7 multiplied by 50 is 60.5. This is a good question. I like those kind of questions because it makes sure that you understand conceptually. It tests you about two different distributions. With this one now, we finished the module on live tables and the little addition on this one. So we finished this whole module. So now I posted or you will find the fourth problem set. So you need to solve all those problems. So you'll have again, in actuarial mathematics, you need to really to practice so many questions to make sure that you are comfortable with those concepts. The more problems you solve, the better you are. And there are lots of questions also available at the SOA.org, site of Actuarial's website, and they have the solutions as well. You can practice, but I think the problems I gave you should be sufficient to prepare you for the exams, as I would bring similar questions to those. All right, good luck.